What is the most powerful thing in the universe? Is it a supernova that outshines an entire galaxy for a moment in time? A black hole that bends space and time into knots? A beam of radiation that could erase a planet in the blink of an eye? Power in the universe comes in many forms. Some of these forces destroy everything in their path. Others quietly hold the cosmos together. And a few are so strange, so extreme, that we still don't fully understand how they work. Let's explore forces that push the limits of what reality can handle. Ultra-high energy cosmic rays, nature's particle accelerators. On occasion, a single particle, smaller than an atom, can strike Earth with more force than a baseball pitched by a professional athlete. Ultra-high energy cosmic rays are among the most powerful subatomic particles ever observed. They don't come in swarms or clouds like stardust or solar winds. Instead, they arrive one by one, like silent microscopic bullets from deep space. Each one is a lone traveler, crossing immense distances to reach us, and when they do, they sometimes release more energy than any human-made machine has ever been able to produce. To put this in perspective, consider the most advanced particle accelerator on Earth, the Large Hadron Collider, or LHC, in Switzerland. It smashes protons together at nearly the speed of light, producing energies of up to 13 trillion electron volts. That's an enormous amount of energy for a single particle, enough to explore the very building blocks of matter. But ultra-high energy cosmic rays laugh at these numbers. Some of them carry energies of over 100 quintillion electron volts. That's millions of times more energy per particle than anything we've managed to build on Earth. Imagine all that power packed into something smaller than a proton. It's almost too much to believe. Most cosmic rays are born in ordinary events like solar flares or exploding stars, and they're relatively low in energy. But these ultra-high energy versions are different. They don't seem to come from anywhere nearby. They must have been accelerated somewhere far, far away, far beyond our galaxy, in some of the most extreme environments in the universe. Supermassive black holes at the centers of galaxies, for example, could be responsible. These monsters spin and twist space around them, shooting out massive jets of particles. Or maybe the cause lies in the aftermath of gamma-ray bursts, the brief but powerful explosions left behind when stars collapse or merge. We've only observed a handful of these rays, and their paths are bent and twisted by magnetic fields as they travel, so tracing them back to their origin is nearly impossible. They don't strike the ground directly. Instead, they hit atoms high in the atmosphere, smashing them apart and creating a cascade of other particles. One tiny particle sets off a shower that can spread over kilometers. Detectors on the ground pick up the secondary particles and try to piece together what happened. In places like the Pierre Auger Observatory in Argentina, scientists use huge arrays of detectors spread out over wide areas to watch for these events. When a cosmic ray hits the upper atmosphere, it sends a wave of particles downward. These detectors listen for that wave and measure its size and shape. It's like trying to figure out what kind of rock made a splash by looking at the ripples in a pond. From the shape of the ripple, they try to learn the size and energy of the original stone. Even though we've built these enormous observatories to study them, ultra-high energy cosmic rays remain rare. On average, only about one of them hits each square kilometer of Earth's surface every century. That means you could watch the sky your whole life and never see one. If we could understand them, we might learn about the most extreme environments in the universe. We might even discover new physics. If space is not completely smooth, but instead has a fine texture at the smallest scales, ultra-high energy cosmic rays could help us detect it. We think of human machines like the LHC as powerful and advanced. And they are. They represent the peak of what we can build. But even these mighty tools are dwarfed by nature's own accelerators. Somewhere out there, in the dark between galaxies, something is hurling single particles with a force beyond imagination, over distances so vast that they defy the mind. The cataclysmic hammer, dynamics of mega-asteroid impacts. Unlike the tiny, invisible cosmic rays that travel alone and unseen, a mega-asteroid is a mountain of metal and stone. The energy released on impact is enormous, far beyond anything that human beings have ever created. A 10-kilometer asteroid striking Earth would release more energy than all the nuclear weapons on the planet combined, not just once, but many times over. The physics is simple but terrifying. A massive object moving at such a high speed carries kinetic energy that must go somewhere when the rock stops. And it stops suddenly, smashing into Earth's crust like a hammer hitting glass. The crust melts. The ground trembles. Shockwaves tear through the rock layers, cracking the surface for hundreds of kilometers. Within seconds, a massive crater forms, deeper than any human-made excavation. The impact itself happens in the blink of an eye, but its effects ripple outward in waves of destruction. The heat alone is enough to ignite fires for thousands of kilometers in every direction. Forests burst into flame. Animals caught in the open don't have a chance. Winds reach hurricane speeds, driven not by weather, but by the blast itself. Dust and debris are thrown high into the atmosphere, and as they fall back to Earth, they superheat the air, turning the sky into an oven. Then come the tsunamis. If the asteroid strikes an ocean, which is likely, given that most of Earth is covered in water, the explosion pushes massive walls of water outwards. These waves are unlike ordinary tsunamis caused by earthquakes. They are much taller, much faster, and much more destructive. Coastal regions on the far side of the planet might be slammed by water hours later, with waves higher than buildings. Nothing near the shores survives. The ocean itself becomes a weapon. The dust and soot thrown up by the impact block sunlight for months, even years. Plants wither, temperatures fall. A kind of artificial winter settles in, not caused by snow or ice, but by the absence of light and warmth. This impact winter starves ecosystems. Without sunlight, plants can't grow. Without plants, herbivores die. Without herbivores, predators starve. Whole food chains collapse. There is one moment in Earth's history when we know this happened. 66 million years ago, an asteroid roughly 10 kilometers across slammed into what is now the Yucatan Peninsula in Mexico. The crater is still there today, buried under layers of rock and sediment. It's over 180 kilometers wide. The asteroid that made it ended the reign of the dinosaurs. Not just because it hit, but because of what came after. This single impact wiped out about 75% of all species on the planet. And it didn't take a long time. Within a few years, life on Earth looked very different. The strong, the lucky, and the small survived. Everything else vanished. The skies cleared eventually. The Earth warmed again. But the damage was done. And this wasn't the only time. Earth has been hit by many smaller asteroids throughout its history. Some were only a few kilometers wide, others less. They didn't all wipe out species, but they left their marks. Craters, broken rock layers, strange mineral formations. Even today, new craters are still being discovered in remote regions. They remind us that these impacts are not just ancient history. They are part of our planet's ongoing story. Scientists are now able to model what would happen if another mega-asteroid were to strike. The results are grim. Even a rock half the size of the one that killed the dinosaurs could cause global devastation. Cities would be vaporized. Crops would fail. International systems, trade, communication, food delivery would fall apart. Modern humans might survive, but only just. Civilization as we know it would be tested like never before. One of the challenges with these impacts is how quickly they happen. A rock could be spotted months or years before impact, or not at all. Many small asteroids pass near Earth every year, and some are only discovered after they've passed us. Larger ones are easier to track, but even then, the warning time might be short. We have telescopes scanning the sky, watching for threats. But space is big, and rocks don't glow. They reflect sunlight weakly and are often lost in the dark until it's too late. Efforts are underway to prepare. Some scientists are working on ways to deflect incoming asteroids, using rockets, solar sails, or even nuclear blasts to nudge them off course. But these methods are still in early stages. We have never had to use them in a real emergency. And even if we had years to prepare, success would not be guaranteed. A 10-kilometer asteroid doesn't need to explode to cause harm. It just needs to land. Despite the danger, there is something awe-inspiring about these cosmic hammers. They are part of how planets evolve. They mix up the crust, bring new materials to the surface, even create habitats in the long term. Some scientists think asteroid impacts helped bring water and organic molecules to early Earth. Without them, life as we know it might never have started. But that doesn't make the threat any less real. These objects don't follow our rules. They don't know we're here. One day, one of them could arrive, fast, heavy, unstoppable. And the Earth, for all its strength and beauty, would quake by the full force of a single rock from space. Rogue planet encounters, collisions beyond the solar system. In the quiet reaches between the stars, there are planets with no sun. They drift alone through space, dark and cold, without the warmth of a star to orbit. Giant, wandering worlds set loose from their home systems. And as they move silently through the galaxy, they sometimes pass near other systems. The chances are small, but not zero. And if one of these worlds were to collide with another planet, especially one the size of Earth or larger, the results would be beyond anything we've ever seen. A collision between planets is not like a rock hitting another rock. These are entire worlds. They have gravity, molten cores, atmospheres, maybe even life. When a rogue planet smashes into another, it's not just an impact. It's a cosmic event. Whole star systems could be reshaped by the force of such a crash. Let's imagine what that might look like. A rogue planet, maybe the size of Earth or even bigger, has been drifting through space for billions of years. It carries its own heat deep inside, left over from its formation, but it has no sunlight. Its surface is likely frozen, covered in ice. Now imagine this planet entering a new system. Maybe it's pulled in by the gravity of a star, or maybe it's passing close to another free-floating planet. Over time, their paths cross. They're on a slow collision course, drawn together by gravity, moving faster and faster as they approach. At the moment of collision, the energy released is more than 1 trillion times greater than the largest nuclear bomb. The surfaces of both planets melt instantly. Mountains are flattened. Oceans vaporize. Atmospheres explode outward into space. The cores of the planets, hot, dense, and full of metal, collide and possibly fuse. The surrounding space is filled with glowing debris, hot plasma, and shattered rock. For a brief moment, the impact shines brighter than many stars. Now think about what happens if a rogue planet collides with an inhabited world. A planet like Earth, filled with oceans, forests, cities, and people. There's no warning siren loud enough for that kind of event. The collision would erase everything, not just civilization, but continents. Even the crust of the planet could be destroyed. Life would not just end. It would be erased completely, buried under molten rock and lost in the chaos of impact. The result is not just destruction, however. It is transformation. The remains of the two planets may merge into one new world, larger and more complex than either was before. A molten, chaotic world spinning rapidly, covered in liquid rock and surrounded by a cloud of debris. Over millions of years, that debris could form rings. Some of it might come back together to make moons. The heat would take eons to fade. But in time, a new planet might emerge from the wreckage, reshaped, rebuilt, and perhaps even ready for life. We don't see events like this in real time. They take too long and happen too far away. But there is evidence that such collisions have happened in the past, even in our own solar system. Take Earth's moon, for example. Many scientists believe it was born from a massive collision. Long ago, a Mars-sized planet, sometimes called Theia, may have hit the young Earth. The impact was so powerful that it tore off a chunk of Earth's outer layer. That debris eventually gathered in orbit and formed the moon. The Earth survived, but it was forever changed. Its tilt, its spin, and even its seasons may have been shaped by that ancient crash. Other planets show signs of trauma too. Uranus is tilted on its side, possibly because of a giant impact early in its history. Mercury has a metal-rich core and a thin outer layer, which may also be the result of a massive collision that stripped away much of its rocky surface. These scars are silent, but they tell us that planet-on-planet impacts are not theoretical. They are part of how solar systems grow up. Scientists estimate that there could be as many rogue planets in our galaxy as there are stars, maybe more. That's billions of worlds drifting through space, untethered, silent, and invisible. Some are the size of Earth. Others may be as big as Jupiter. They don't need to hit another planet to cause trouble. Just passing nearby could pull orbits out of balance. It could disturb comets, trigger asteroid storms, or knock moons off course. But if one of these planets hits, it's not a crack or a dent. It's a reset button. Electron capture supernovae, the understudied stellar explosions. Most people, when they hear the word supernova, think of the classic kind. A massive star, bigger than 10 times the Sun, builds up an iron core that can no longer support the weight of everything above it. Gravity takes over, and in less than a second the core collapses. The outer layers come crashing in, bounce off the compressed core, and get blown outward in a massive explosion. That's the textbook supernova. But there's another kind. It's quieter, rarer, stranger. It doesn't rely on iron. It doesn't come from the biggest stars. Instead, it comes from stars that are somewhere in the middle, not small enough to fade peacefully, but not large enough for the usual explosion. These stars, usually between 8 and 10 times the mass of our Sun, die in a way that has only recently begun to be understood. The process is called an electron capture supernova. In these stars, the core doesn't fill with iron. Instead, it builds up with elements like oxygen, neon, and magnesium. The star lives its life in relative quiet, fusing lighter elements into heavier ones and slowly gathering more and more mass in the core. But one day, something unusual happens. Inside the dense core, electrons, normally buzzing around atoms or helping to carry energy through a star, begin to disappear. They are pulled into the hearts of atoms, where they combine with protons and turn into neutrons. This process, called electron capture, changes the balance inside the star. Electrons help hold up the star by creating outward pressure. When enough of them vanish, the pressure drops, and once it does, there's nothing left to stop gravity. The collapse is sudden. The core falls in on itself. The outer layers rush inward. Temperatures soar. Neutrons get packed together tighter than in anything else in the universe. And then, as all that falling matter slams into the hard neutron core at the center, the shockwave turns outward, blasting the star apart. Electron capture supernovae may not be as bright or as violent as iron core collapse supernovae, but they carry clues about the early universe, about star formation, and about how heavy elements are spread through galaxies. These explosions can send rare isotopes flying across space. These events are hard to find. They don't happen often, and when they do, they can look a lot like other kinds of supernovae. It takes careful observation to notice the differences. Light curves, the way the brightness changes over time, can be just a little bit slower. The chemical signatures in the light, when analyzed with special tools, show traces of elements you wouldn't expect from other explosions. Now, with new telescopes and better models, researchers are finally able to see what's happening. Electron capture supernovae appear to be a special doorway between quiet endings and violent ones. They may be responsible for creating certain neutron stars with very specific masses. They could also explain strange chemical patterns found in some old stars. These mid-mass stars, which used to be ignored in favor of their heavier or lighter cousins, are now seen as an important piece of the cosmic puzzle. They may help explain how elements like oxygen and magnesium are recycled into new generations of stars and planets. In some cases, they may even play a role in triggering the birth of new stars by sending shock waves through nearby gas clouds. Electron capture supernovae seem to happen only under very specific conditions. The star must be in a narrow mass range. The core must be just the right mix of elements. And the timing of the collapse depends on delicate balances: how fast mass is added, how hot the core gets, and how quickly electrons are captured. Too much mass, and the star becomes an iron core supernova. Too little, and it turns into a white dwarf. Only a narrow path leads to this quiet kind of catastrophe. The neutron stars that result from electron capture supernovae may spin more slowly, have weaker magnetic fields, and carry different compositions compared to their more dramatic cousins. They might even be responsible for some of the quiet neutron stars we observe, those that don't flash brightly or shoot out intense radio waves, but simply sit, cold and faint, as leftovers from a less flashy end. Pair instability supernovae, stars exploding from within. Some stars are born so massive, so bright and so hot that the usual rules of stellar death don't apply. These stars, dozens to hundreds of times more massive than our Sun, push the limits of what physics can handle. Their lives are short, only a few million years at most. but their ends are some of the most violent in the universe. And for a few of them, death doesn't come from a collapsing iron core or even from running out of fuel. Instead, these stars explode not because they're weak, but because they're too strong. They destroy themselves from the inside out in what's known as a pair instability supernova. To understand how this happens, we have to look deep into the heart of a star. In the center, where temperatures reach hundreds of millions of degrees, the star fuses lighter elements into heavier ones. Hydrogen becomes helium, helium becomes carbon, then carbon becomes oxygen, and so on. Each time the core gets hotter, new elements are formed, and energy is released. This energy pushes outward, balancing the weight of the star's own gravity. The star stays stable because the heat pushing out matches the weight pressing in. But in the most massive stars, as the core grows hotter, reaching billions of degrees, the light itself, the radiation that normally holds the star up, starts to behave differently. Instead of just being a steady force pushing outward, it begins to change form. The photons start turning into pairs of particles and antiparticles, electrons and positrons. When light becomes matter and antimatter, it stops doing its job. Radiation pressure drops. Gravity, which has always been waiting for its moment, takes over. The balance is broken. The core contracts. The pressure builds. And in a blink, the entire star can ignite in one massive runaway fusion reaction. Unlike a normal supernova, which collapses before it explodes, this one explodes without collapsing. The sudden fusion of oxygen, neon, and other heavy elements floods the core with energy. Temperatures spike. The whole star is torn apart from within. There's no neutron star left behind, no black hole, just a vast expanding cloud of gas and elements rushing into space at thousands of kilometers per second. This is a pair instability supernova, and it's one of the only ways a star can die that leaves nothing behind. This type of explosion doesn't come from reaching the end of fusion. It doesn't come from running out of fuel. It comes from the way high-energy photons can turn into mass. It's a chain reaction where the star's own light becomes its enemy. The more massive the core, the hotter it gets. The hotter it gets, the more light turns into particles. And the more particles form, the less radiation pressure is left to hold the star up. It's a feedback loop that ends in total destruction. These explosions are rare. They only happen in stars with very specific masses, somewhere between 130 and 250 times the mass of the Sun. If the star is smaller, it might survive, even if only briefly. If it's larger, the collapse might go so deep and fast that the star becomes a black hole instead, skipping the explosion altogether. Unlike other supernovae, they don't just scatter small amounts of heavy elements. They release huge quantities of elements like oxygen, carbon, silicon, and even some iron into the surrounding space. These elements can then become part of new stars, planets, and even life. Astronomers have long suspected that these explosions were more common in the early universe. The first generations of stars, called population 3 stars, were thought to be more massive and more metal-poor than stars today. Without many heavy elements to help cool the gas, stars in the early universe could grow extremely large. Some of them likely ended their lives in pair instability supernovae, scattering their materials into the newborn galaxies around them. We may be seeing the light of these ancient explosions even now. The James Webb Space Telescope, with its ability to see into the early universe, is searching for signs of such events in galaxies more than 13 billion light-years away. Even in our local universe, astronomers have found candidates for modern pair instability supernovae. One example is SN 2007 Bi, an unusually bright supernova that appeared in a distant dwarf galaxy. Its light lasted longer than normal, and its spectrum showed a large amount of nickel, a clue that a very massive star had exploded completely without leaving a remnant. It matched the models for a pair instability supernova almost perfectly. It may have been one of the first clear examples seen in real time. Another possible candidate is the even more extreme SN 2213 to 1745, a superluminous supernova whose light took billions of years to reach us. It burned brighter and longer than typical supernovae, and may have been caused by a similar mechanism. These events are still being studied. New observations and improved models are helping scientists figure out which explosions truly match the pair instability profile. These explosions are important for understanding cosmic chemical evolution. They help explain how certain elements, especially in small metal-poor galaxies, could appear in large amounts. When one of these stars explodes, it seeds its surroundings with the ingredients needed for future stars and planets. It may even help explain why some ancient stars in our galaxy show signs of heavy elements that shouldn't be there, unless something this powerful had occurred billions of years ago. Colliding giants, the mechanics of stellar mergers. Some stars live in pairs, orbiting one another. These pairs, known as binary systems, are common throughout the galaxy. Sometimes the stars in these systems are nearly the same size. Other times, one may be much larger, hotter, or older than the other. But in certain cases, these stars draw closer and closer over time. Their orbits shrink, their speeds increase, and eventually they can no longer stay apart. They crash into each other. This is a stellar merger, two live stars slamming together in a fiery, chaotic embrace. The process begins slowly, often over millions or even billions of years. Two stars orbit one another, but they are not perfectly still. Stars, like anything with mass, lose energy. That energy can be lost in the form of gravitational waves, ripples in the fabric of space itself, or through interactions with outer gas layers if the stars are close enough. As energy leaves the system, the stars spiral inward and their orbits grow tighter. If nothing interrupts this process, if the stars don't explode first or throw each other apart, then collision is inevitable. Stars are made of gas and plasma. When they touch, their outer layers begin to mix. The gravitational pull between them grows stronger. They stretch and deform, pulling at each other's atmospheres. Eventually, the distinction between the two stars disappears. They begin to swirl into each other, forming a single, larger, and often very unstable object. What happens next depends on the type and mass of the stars involved. If the stars are similar in size and still burning hydrogen in their cores, the result can be a new, more massive star. This star can shine brighter and live shorter than either of the original stars would have on its own. It may appear as a blue straggler, a type of star that looks too young and bright for its place in an old star cluster. Astronomers believe many blue stragglers are the result of past mergers, their youthful glow hiding the violent event that created them. But not all mergers are so neat. If one or both of the stars are older, if one has become a red giant, or if they are uneven in mass, the process can become messy. The larger star may swell and absorb the smaller one. Their cores might stay separate for a while, orbiting inside a shared outer envelope. This phase is known as a common envelope, and it's one of the most complex and unstable moments in stellar evolution. During the common envelope phase, friction between the cores and the surrounding gas can heat the system and cause the envelope to puff out or even get ejected into space. What's left behind could be a close binary of two cores, or a single star if the merger completes. Sometimes, the energy released is enough to create a luminous red nova, a burst of light less powerful than a supernova, but still bright enough to be seen across the galaxy. These luminous red novae are rare, but they have been observed. One of the most famous occurred in 2008, when a star in the Andromeda galaxy suddenly brightened for weeks before fading away. Observations showed signs that it wasn't a regular supernova. The light curve was slower and cooler. The debris moved at lower speeds. Everything pointed to a stellar merger. Another example occurred closer to home in our own Milky Way. A star system known as V1309 Scorpii suddenly grew brighter in 2008. Archived data showed that the system had once been a contact binary, two stars so close they shared an atmosphere. Then, just before the brightening, the two stars merged. The sudden glow was the moment of final contact. It gave scientists a rare chance to see the exact timeline of a merger, from two stars orbiting tightly to one star shining from the aftermath. When the stars involved in the merger are more massive, the results can be even more dramatic. A merger between two giant stars can cause extreme outbursts. Their combined cores may ignite new layers of fusion. The sudden mixing of elements can create flashes of light, unusual chemical signatures, and in some cases, a new round of stellar activity. These massive merged stars might live fast and die young, ending their lives in supernovae far sooner than they would have on their own. In some rare systems, two stars may merge and leave behind more than just one massive star. They can give birth to exotic systems like magnetars, ultramagnetic neutron stars, or even rapidly spinning pulsars. The precise mechanics depend on the masses, chemical makeup, and timing of the merger. Each collision is different. Each leaves behind a unique fingerprint. Some stellar mergers may even result in gamma-ray bursts, among the most energetic events in the universe. Though more commonly associated with neutron star mergers, there is evidence that certain long gamma-ray bursts might arise from the collapse of massive merged stars. The theory is that when two stars merge into a single ultramassive object, it may rotate so rapidly that upon collapsing, it sends out narrow beams of high-energy radiation. If those beams point toward Earth, we can see them as intense bursts of gamma rays lasting several seconds. In dense star clusters, where stars are packed closely together, gravitational interactions can cause stars to drift into each other's paths more often. Older clusters with thousands or millions of stars increase the chances of mergers. It's likely that many of the most massive stars we observe in such clusters were formed from earlier mergers. Even in the future of our own solar system, a type of stellar merger is expected. Billions of years from now, the Milky Way and the Andromeda Galaxy will collide. When that happens, stars won't crash into each other directly. The space between them is too vast, but their orbits will shift. Some systems may become destabilized. Binary stars might spiral together, and some will merge as a result of the galactic upheaval. Neutron star densities, crushing gravity in a pinch. A neutron star is the crushed core left behind when a large star dies in a supernova. These stars are incredibly small by cosmic standards, usually no more than 20 kilometers across, which is about the size of a city. But inside that small sphere is more mass than our entire sun. That much matter packed into such a small space results in gravity so strong that nothing on Earth compares. If you stood on the surface of a neutron star, you would feel gravity billions of times stronger than Earth's. You wouldn't just be pulled down, you'd be crushed in a fraction of a second, your atoms torn apart by the pressure. The key to this pressure is density. On Earth, density usually refers to how heavy something is compared to its size. A rock is denser than a sponge. Water is denser than air. But neutron stars go far beyond anything we can make on Earth. In fact, the density inside a neutron star is so high that atoms themselves are no longer normal. Electrons and protons are forced together into neutrons. These neutrons are then packed shoulder to shoulder, with hardly any space between them. A single teaspoon of neutron star matter would weigh around 10 million tons. That's not an exaggeration. It's more than the weight of every building in a large city. The surface is thought to be made of a thin crust, maybe just a few hundred meters thick, made of atoms that are stretched into long, rigid chains by gravity. Beneath that crust, things get stranger. The deeper you go, the more the pressure grows. Neutrons start to behave like a strange kind of fluid, flowing in ways we can't easily predict. Inside, the pressure becomes so intense that it warps space itself. Time ticks more slowly near a neutron star, just as Einstein predicted. Light from the surface bends under the force of gravity, curving its path even as it escapes. In fact, from a certain distance, you can see more than half the surface of a neutron star at once because the light is bent so sharply around it. It's like seeing a ball from the side, but also catching a glimpse of its back all at once. Because they're so dense, neutron stars rotate very quickly. Many of them spin several times per second. Some spin hundreds of times per second. These spinning neutron stars, called pulsars, send out beams of radio waves or X-rays as they turn. Each beam sweeps across space like a lighthouse. When one of these beams passes Earth, we detect a pulse. These pulses are so regular that they rival atomic clocks in their precision. In fact, some pulsars are used to track time in scientific experiments. The strong gravity also affects what falls toward the star. If you dropped a pebble onto a neutron star, it would hit the surface at about half the speed of light. That much energy released in a tiny area would create a burst of heat, light, and radiation. Even something as small as a grain of sand would release an enormous amount of energy when it hit. This is one reason why binary systems containing neutron stars can be so bright. If a neutron star is pulling matter off a nearby companion star, the falling material releases huge amounts of energy as it crashes into the surface. Scientists still aren't sure exactly what's inside the very center. Some theories suggest that the neutrons break down into even smaller particles, quarks, and form a core of exotic matter. Others propose that new types of particles, like hyperons, could appear. These possibilities are hard to test because we can't replicate such extreme conditions on Earth. To understand what holds up a neutron star, we look at what's called neutron degeneracy pressure. This is a quantum effect. Neutrons, like electrons, follow something called the Pauli exclusion principle. This rule says that no two identical particles can occupy the same state at the same time. As neutrons are packed closer together, they start to resist further compression, not because of electric charge, but because of this quantum rule. This degeneracy pressure is what prevents the star from collapsing completely into a black hole, at least up to a certain mass. However, there is a limit. If the neutron star becomes too massive, about 2 or 3 times the mass of the Sun, it can't hold itself up anymore. At that point, gravity wins, and the star collapses further into a black hole. This is why neutron stars and black holes are closely linked. One is often the final stop before the other. Despite their small size, neutron stars also have incredibly strong magnetic fields. In some cases, these magnetic fields are trillions of times stronger than Earth's. These ultramagnetic neutron stars are called magnetars. Their magnetic fields are so intense that they can twist and snap, releasing huge flares of energy. One such flare, if aimed at Earth from a few light years away, could cause damage to our atmosphere. Luckily, there are no known magnetars close enough to pose a danger. Every now and then, we get lucky. A neutron star in a binary system spirals toward its partner, or merges with another neutron star, sending out gravitational waves we can detect. These events give us rare glimpses into the lives of these strange objects. But most of the time, neutron stars remain silent reminders of the violent pasts of once bright stars. The Quark Nova conjecture, a hypothetical second blast. For decades, it was thought that matter couldn't be packed more tightly than in a neutron star, unless it collapsed into a black hole. But the Quark Nova idea asks, what if that's not entirely true? What if the pressure inside a neutron star continues to rise, maybe because the star gains more mass, or because conditions inside shift just enough to push it over a new limit? At that point, the theory says, neutrons themselves could break apart. Under enough pressure, they could dissolve, freeing their quarks into a new, exotic state of matter. This is called quark matter. It's not made of neutrons or protons anymore. It's just raw quarks, up, down, and maybe even strange quarks, flowing in a dense soup. The change from neutron matter to quark matter is not gentle. It would cause a sudden collapse and a bounce back, like a rubber ball squeezed too hard. The result would be a second explosion, a quark nova. This new blast would follow the original supernova, perhaps hours or days later, blasting out more energy, more particles, and reshaping the remains of the dying star. If real, it could be responsible for certain strange features seen in the light from distant supernova. Some supernovae don't fade as expected. Instead, they seem to brighten again briefly, or show unusually strong emission lines. These odd light patterns could be signs of 2 explosions. First the supernova, then the quark nova catching up and interacting with the material thrown out earlier. Some models suggest that the second explosion might send out fast-moving jets of particles or release powerful gamma rays. It might even help explain some of the brightest supernova ever recorded. events that shine 10 or 100 times brighter than normal ones. During a normal supernova, many heavy elements are forged, but in the incredibly dense neutron-rich environment of a neutron star, even heavier and rarer elements might form. If a quark nova explodes and mixes with this material, it could scatter unusual atomic signatures into space. These could show up in the spectra of old stars, or in the dust that makes up future solar systems. There's also a strange byproduct of the process: strange quark matter. Some scientists have proposed that once quark matter forms, it could be more stable than regular neutron matter. If that's true, then once a bit of strange quark matter appears, it could spread, turning nearby neutrons into more quark matter. This chain reaction would convert the whole core of the neutron star into a quark star. Quark stars remain hypothetical. No one has directly observed one, but they're one possible end state for matter under extreme pressure. A quark nova might be the key process that creates them. If these stars exist, they would be even smaller and more exotic than anything else we've seen. They might shine differently, spin differently, or emit strange signals. There are even ideas that strange quark matter could break off during a quark nova and fly through the galaxy in tiny fragments. These strangelets would be tiny, ultra-dense pieces of matter. If one ever passed through our solar system, it might leave behind a small but measurable signal. One of the challenges is that we don't yet fully understand the behavior of quark matter. On Earth, we've only seen it briefly in high-energy particle collisions. Even then, it only lasts for a fraction of a second. Studying it in stars would require instruments that can read the signatures of particles and radiation from millions of light years away. Still, the theory offers a powerful new lens for viewing the final moments of stars. If quark novae do exist, they would rank among the most intense and exotic events in the cosmos. And they would show that even in the heart of a star that's already exploded, something deeper can still break free, something smaller than neutrons, and powerful enough to rip the core apart one last time. Kilanova explosions, heavy element forges in neutron star mergers. In the quiet corners of the universe, two neutron stars can orbit each other for millions, even billions of years. From far away, their movement appears smooth and steady. But over time, gravity pulls them inward, their orbits shrink, their speed increases, and then, one day, with no warning, they collide. The result is one of the most powerful and unusual explosions the universe can offer, a kilanova. This kind of event is rare. It doesn't happen as often as a regular supernova. As the two stars orbit, the system gives off gravitational waves. These waves carry away energy, which causes the stars to spiral closer. Eventually, the distance between them becomes so small and their speeds so high that they can no longer stay in separate orbits. They crash together in a final, violent merger. The explosion that follows is called a kilanova. For a brief time, the matter thrown out from the merger becomes a forge for some of the heaviest elements in the universe: gold, platinum, uranium. These are not made in normal stars. They are too heavy and need conditions that only exist in extreme events like this. When the neutron stars crash into each other, they tear themselves apart. Huge amounts of matter are flung outward at high speeds. This matter isn't like normal gas or dust. It's neutron-rich, meaning it contains far more neutrons than ordinary elements. In the outer layers of the explosion, the temperature and pressure are just right to allow these free neutrons to slam into atomic nuclei. This process is called rapid neutron capture, or the R process. The R process builds heavier and heavier elements step by step. It starts with something small like iron and adds neutrons one after another. Some of these neutrons then turn into protons, changing the element. In a matter of seconds, entire chains of heavy elements are formed. This is where many of the rarest elements in the universe come from. Gold and platinum are two of the most famous examples. Without kilanovas, these elements would be far less common, perhaps even missing from our solar system entirely. The light from a kilanova doesn't look like a supernova. It rises quickly, within a day or two, and then fades over a week or so. It glows in a strange way, with colors shifting from blue to red as the heavy elements begin to form and cool. The opacity of the ejector, how much light it blocks, also changes. At first, the explosion is bright and hot. Then, as more complex elements form, the material becomes thicker and cooler, hiding some of the light. In 2017, astronomers got their first confirmed look at one of these events. Two neutron stars merged in a galaxy about 130 million light-years away. It was the first time we detected both gravitational waves and visible light from the same source. The gravitational waves arrived first. Then telescopes around the world turned to the same patch of sky and saw the light of the Kilanova. From Earth, the explosion appeared as a faint flash in a distant galaxy. But in that moment, dozens of Earth masses of heavy elements were created. Some estimates suggest that a single Kilanova can make enough gold to fill Earth's oceans many times over. It doesn't happen often, but it doesn't need to. Just a few of these explosions can seed entire regions of space with the building blocks of rare materials. What happens after the merger depends on how much mass was involved. Sometimes, the two neutron stars collapse directly into a black hole. Other times, they may form a very massive neutron star that lives for a short while before also collapsing. During this time, magnetic fields and rotation can power strong jets of material that shoot out into space. These jets can move near the speed of light and are responsible for brief bursts of gamma rays, known as short gamma ray bursts. Unlike longer gamma ray bursts, which come from massive stars collapsing into black holes, these shorter ones are linked to neutron star mergers. They last only a couple of seconds, but release more energy than the Sun will produce in its entire lifetime. With the help of gravitational wave detectors like LIGO and Virgo, scientists can now pinpoint likely events and alert telescopes quickly. Each new observation adds more detail to the picture. By studying the light, the timing, and the chemical fingerprints in the spectra, scientists can learn how the elements form and how the explosion evolves. Even today, much of our solar system's gold likely came from one or more kilanovas that occurred long before Earth existed. Over time, the elements drifted through space, mixed into clouds of gas and dust, and helped form the planets. In that sense, these rare explosions shaped not just distant galaxies, but the materials we use every day. And yet, there is still much we don't know. How common are these events, really? Do they always make the same mix of elements? What happens to the leftover core? As detection tools improve, more kilanovas will be found. While we may never see one up close, we carry their results with us, worn on fingers, hidden in circuits, scattered through stone. All from the sudden, silent death dance of crushed stars colliding in the dark. Magnetar giant flares, magnetic fields beyond imagination. There are few things in the universe more intense than a magnetar. Their magnetic fields are the strongest known in the entire cosmos. A single magnetar can carry a magnetic field 1,000 times stronger than that of a normal neutron star, reaching up to a quadrillion times stronger than Earth's. These fields are so powerful that they don't just influence nearby space, they can reshape matter itself. The field of a magnetar is so strong that it can affect atoms at the quantum level. Electrons are forced into narrow paths. Light can behave strangely near such a field, becoming polarized or scattered in unusual ways. Even empty space is not left untouched. According to quantum theory, space near a magnetar's surface can behave like a prism or a lens, bending light in ways that don't happen anywhere else. Most of the time, magnetars are quiet. They rotate slowly compared to other neutron stars. Some spin once every few seconds. They give off low levels of X-rays or gamma rays, just enough to be noticed from Earth by specialized telescopes. But then, without warning, they can erupt. These eruptions are known as giant flares. A magnetar might go years without activity, then in less than a second release more energy than our Sun gives off in 100,000 years. These flares are not caused by nuclear fusion or even gravitational collapse. They are caused by the magnetic field itself. Over time, the powerful field of a magnetar twists and shifts. It strains the solid crust of the neutron star. just like the Earth's crust can crack during an earthquake, the crust of a magnetar can snap. When that happens, the energy stored in the twisted magnetic field is released all at once. The result is a sudden, massive outburst of gamma rays and X-rays, sometimes accompanied by a rearrangement of the star's magnetic field lines. These bursts are so strong that even from tens of thousands of light years away, they can be detected on Earth. One of the most famous magnetar flares was recorded on December 27, 2004. It came from a magnetar called SGR 1806-20, located about 50,000 light-years from Earth. The initial flash of gamma rays was so intense that it temporarily changed the shape of Earth's ionosphere. Satellites designed to detect nuclear weapons went off, thinking a detonation had occurred. The flash lasted only a fraction of a second, but its energy overwhelmed detectors. If the magnetar had been only a few dozen light-years away, it could have caused real damage to Earth's atmosphere. But these flares are rare. Since observations began, only a handful of giant magnetar flares have been seen. Most flares are smaller, less violent events, often called bursts. These might happen more regularly, especially when the star is young and its magnetic field is still evolving. Even these smaller bursts can rival the energy output of our Sun, but they are shorter and more localized. Scientists study magnetars not just because of their power, but because they seem to exist at the edge of what's physically possible. The strength of their fields challenges the limits of quantum theory and general relativity. No laboratory on Earth can come close to creating conditions like those found on or near a magnetar. They are natural experiments in extremes of gravity, pressure, and magnetism. There is also the possibility that some mysterious signals from space, known as fast radio bursts, or FRBs, could be related to magnetars. These are powerful radio pulses that last just milliseconds. Some come from repeating sources. Others are one-time events. In 2020, a magnetar in our own galaxy was seen to emit a radio burst at the same time it gave off X-rays. It wasn't as strong as the FRBs detected from far away, but it gave scientists a clue that these bizarre objects might be connected to that larger mystery. Magnetars are not expected to live long. Their magnetic fields decay over time, and as that happens, the activity slows down. In a few thousand years, they may become quiet neutron stars, still spinning but no longer flaring. This makes them hard to find. Only a couple dozen magnetar candidates are known today. They are scattered across the galaxy, their locations identified by bursts of high-energy radiation that appear and vanish again before anyone can look twice. Satellites like NASA's Swift and Fermi missions constantly scan the sky for high-energy flashes. When something triggers an alert, telescopes across the globe swing into position to try to catch the fading afterglow. Sometimes there's nothing. Other times the burst is traced back to a known magnetar. There is still much that isn't understood. No one knows exactly how magnetars form or why some neutron stars develop such intense magnetic fields while others do not. Some theories suggest they are born that way, from very massive stars with fast spins. Others suggest that interactions after the supernova, like fallback material or binary star companions, may play a role. Either way, once the magnetar forms, it becomes a kind of ticking time bomb waiting to crack. Fast radio bursts, millisecond flashes of incredible power. First detected in 2007, FRBs immediately caught the attention of scientists. They were discovered when astronomers were analyzing archival data from the Parkes Radio Telescope in Australia. A peculiar signal popped up that couldn't be explained by anything known. It was sharp, clear, and came from deep space. It wasn't just a blip, it was a strong and sudden pulse of radio waves, lasting only a fraction of a second. Over the next decade, more FRBs were found, each one a unique puzzle. What makes FRBs so perplexing is their brevity and power. While other radio signals from space, such as those from pulsars or quasars, are usually consistent and predictable, FRBs seem to arrive out of nowhere, with no clear pattern. They can't be traced to any familiar source. Unlike more familiar cosmic objects that release steady emissions over long periods, FRBs appear and vanish in the blink of an eye. These flashes are so intense that they can release as much energy in a millisecond as the sun does in an entire day. And yet, when astronomers look at the point in space where an FRB originates, they find nothing visible. No accompanying bright light, no visible star, no black hole, just radio waves. The first few FRBs were suspected to be some kind of technical glitch, but as more were discovered, the idea of a malfunction was ruled out. These signals were real and coming from somewhere far away, far beyond our solar system. Their extreme energy and sudden appearance made it clear that whatever caused them was both unique and powerful. As astronomers continue to search for answers, several theories have emerged about the origins of FRBs. The most common theory is that these radio bursts are related to the explosive events that occur in the death throes of massive stars or the collapse of extremely dense objects. One possibility is that FRBs might be the result of a neutron star or a magnetar. Magnetars, as previously mentioned, are known to produce high-energy flares when their intense magnetic fields snap. It's possible that FRBs could be a manifestation of a similar magnetic instability, only occurring on a much larger, more energetic scale. Another theory suggests that FRBs could be the result of a cataclysmic event involving black holes, like the collision of two massive black holes, or a black hole consuming a neutron star. The immense gravitational forces generated during these interactions could cause violent releases of energy that manifest as these fast, powerful radio bursts. However, this theory is still speculative, as no direct evidence has been found linking black holes with FRBs. There are also theories that point to more exotic possibilities. Some scientists have considered the possibility that these radio bursts might be signals or transmissions from advanced extraterrestrial technology. While the likelihood of this explanation is still debated, the sheer unpredictability of FRBs makes the notion worth entertaining. However, as of now, there's no concrete evidence to support the idea that FRBs are artificial in origin. One of the most fascinating aspects of FRBs is their frequency. The bursts are found to have different qualities depending on their origin. Most FRBs appear as single flashes of radio waves, but some repeat. A small number of FRBs have been observed to burst again and again, though they do so at random intervals. This repetitive nature is unlike most other transient astrophysical events, which are typically one-off occurrences. The discovery of repeating FRBs has given astronomers a better chance to study these enigmatic signals, allowing them to start piecing together clues about where they come from and what causes them. Every FRB detected so far has come from outside the Milky Way galaxy. This means that they likely originate from sources billions of light-years away, possibly in distant galaxies. The sheer distance is one of the reasons why these bursts are so mysterious. The fact that something so far away can create a flash so powerful challenges our understanding of how energy can be generated in the universe. The farther away these bursts come from, the harder it is to figure out what kind of object could be responsible for such powerful explosions. Moreover, these radio waves are affected by the material they pass through. As FRBs travel through the intergalactic medium, they interact with electrons and plasma along the way. This causes some of their signals to slow down, stretch, and scatter. By studying the delays in the arrival of different frequencies of radio waves, scientists can learn more about the nature of the space between galaxies. This has provided valuable insights into the makeup of the intergalactic medium, showing us how matter and energy are distributed across vast distances. Repeating signals suggest that the source is not a one-time catastrophic event like a supernova or a black hole merger. Instead, it implies an object or a phenomenon that is capable of producing multiple bursts of energy over time. This has led to further theories, including the possibility that these FRBs are related to highly active magnetars or neutron stars in a binary system, where the intense magnetic fields of the stars create periodic bursts of energy. These bursts could be tied to the internal processes of the star, such as magnetic field changes, or the movement of matter inside the star. Observatories and telescopes worldwide, like the Canadian Hydrogen Intensity Mapping Experiment and the Arecibo Observatory, are constantly on the lookout for these mysterious signals. Black hole formation, the intense power of gravitational collapse. When a massive star's core runs out of fuel, the nuclear fusion reactions that provide the star's outward pressure cease, and gravity begins to take over. The core begins to collapse under its own weight. For very large stars, the collapse is so intense that even the neutrons, which normally keep a neutron star stable through neutron degeneracy pressure, can no longer resist the pull of gravity. This is the moment when the core's collapse speeds up. The gravity becomes so strong that it overwhelms all other forces, and the core continues to shrink, becoming denser and denser. As the core contracts, it reaches a point where the density is infinite and the laws of physics as we know them break down. The result is a singularity, an object where the mass is concentrated in an infinitely small space, creating an infinitely strong gravitational field. The event horizon forms around the singularity, marking the boundary beyond which nothing can escape. This is the point of no return, where the gravitational pull becomes so strong that anything crossing it is inevitably drawn toward the singularity. This boundary marks the formation of a black hole. While the black hole itself is hidden behind the event horizon, the process of its creation can be observed through the violent shock waves and energy released during the supernova. The energy from the collapsing star is released in multiple forms: neutrinos, radiation, and kinetic energy in the form of shock waves. These shock waves can trigger further star formation in the surrounding interstellar medium, dispersing heavy elements into space, which will eventually become the building blocks of new stars, planets, and even life. Every time a massive star reaches the end of its life, this process unfolds, and the cycle of stellar birth and death continues. Each black hole that forms carries within it the secrets of its star's final moments, a lasting reminder of the forces that shape the universe. If the star is not massive enough, its core may collapse into a white dwarf or a neutron star instead of continuing all the way to a black hole. The specific details of black hole formation depend on the mass of the star, its composition, and other factors such as rotation and magnetic fields. Many black holes exist in binary systems, where they are accompanied by a companion star. The black hole can pull material from its partner star, forming an accretion disk of gas and dust around it. As this material spirals toward the black hole, it heats up and emits X-rays and other radiation. These X-rays can be detected by astronomers and used to study the black hole's properties. In some cases, black holes in binary systems may eventually merge with other black holes, creating a more massive black hole in the process and emitting gravitational waves that ripple through the fabric of space-time. The formation of black holes has deep implications for our understanding of the universe. The extreme gravity near a black hole warps space and time, creating conditions that challenge our understanding of physics. At the event horizon, time itself slows down relative to the outside world, and the laws of physics as we know them seem to break down. The singularity at the heart of the black hole is a place where the density of matter becomes infinite and the usual equations of physics cannot explain what happens. Each black hole is a reminder of the unfathomable depths of space and the mysteries that still lie beyond our grasp. Black hole hyperaccretion, supercritical feeding frenzies. Black hole hyperaccretion is a phase where black holes feed at rates far beyond their usual capacity. In this overeating state, the black hole's accretion disk becomes supercharged, with material spiraling inward at astonishing speeds. The feeding frenzy is so intense that it generates massive jets of energy and radiation, making these black holes some of the most powerful objects in the universe. The process begins when matter, gas, dust, and even stars fall into the black hole's gravitational grasp. As the material spirals closer and closer to the event horizon, it speeds up and heats up, emitting vast amounts of radiation. However, under normal circumstances, black holes can only feed at a moderate pace, pulling in matter at rates that are steady but not excessive. But every so often, When there is a large influx of material, either from a companion star or a nearby gas cloud, the accretion disk becomes incredibly dense. The material starts to pile up, and the black hole's gravity pulls it in faster and faster. This leads to an acceleration in the feeding process, with the black hole devouring material at a rate thousands of times higher than normal. The resulting accumulation of energy and matter creates a spectacle of cosmic proportions. During this intense feeding phase, the material in the accretion disk becomes heated to extreme temperatures, often reaching millions of degrees. The friction and pressure in the disk cause it to glow brightly, emitting light across the entire electromagnetic spectrum, from X-rays to visible light. This emission is so powerful that it can outshine the combined light of an entire galaxy. In some cases, the radiation from the disk is so intense that it can even push away some of the material, creating a sort of feedback loop. This forces the black hole to temporarily pause its feeding, allowing the accretion process to stabilize before starting again. One of the most striking features of black hole hyperaccretion is the formation of jets. These jets are streams of highly energetic particles that are ejected from the black hole's poles, moving at nearly the speed of light. These jets are not matter that's being sucked into the black hole, but rather material that is being expelled outward from the region around the black hole. These jets are driven by the powerful magnetic fields generated by the spinning black hole and the accretion disk. As the material in the disk gets pulled into the black hole, it can get trapped in the magnetic fields, which cause it to spiral outward, forming these jets. These jets can be seen from vast distances. In fact, some of the most distant objects we observe in the universe are active galactic nuclei, supermassive black holes at the centers of galaxies that are undergoing hyperaccretion. The energy emitted by these jets is so intense that it can stretch across millions of light years. And in some cases, these jets are the dominant feature of the galaxy. The energy carried by the jets is vast. Each jet can carry away a significant fraction of the energy being produced by the accretion disk, making them one of the most energetic phenomena in the universe. Hyperaccretion also leads to the production of intense radiation. As matter spirals in toward the event horizon, it is compressed and heated to such an extreme degree that it emits X-rays and gamma rays. These types of radiation are the most energetic forms of light and can only be produced in environments where the energy densities are extraordinarily high. The radiation from a hyperaccreting black hole is so intense that it can easily ionize atoms and strip electrons from their orbits, creating a highly energetic environment. The energy released during these feeding frenzies can disrupt the surrounding environment. The powerful jets that are ejected from the poles of the black hole can heat the gas and dust in the surrounding area, preventing it from collapsing into new stars. This process is thought to be one of the ways that black holes can regulate the growth of galaxies. Quasars, the most luminous objects in cosmic history. The term quasar is short for quasi-stellar radio source, a reference to the fact that when they were first discovered, they appeared to be point-like sources of radio waves, much like stars. However, further research showed that they were not stars at all, but rather distant galaxies, whose centers were dominated by an active, supermassive black hole. The energy emitted by a quasar can be many times brighter than the combined output of the stars in the galaxy it resides in, which is why they can outshine their host galaxies by such a vast margin. The discovery of quasars in the 1960s was a groundbreaking moment for astronomy, as they represented a new class of celestial objects that were completely different from anything that had been observed before. Their brightness, energy output, and the fact that they could be seen at such incredible distances pushed the limits of what astronomers thought was possible. Quasars are not static objects. They evolve over time. In fact, the life cycle of a quasar is closely linked to the evolution of its host galaxy. When a quasar is active, it indicates that the supermassive black hole at its center is feeding, drawing in material from the surrounding environment. However, over time, the rate at which the black hole consumes material can slow down, and the quasar can eventually turn off. When this happens, the once bright core of the galaxy fades, and the active galactic nucleus becomes dormant. The material around the black hole may continue to spiral inward, but at a much slower rate, and the energy output of the system diminishes. It's also worth noting that not all supermassive black holes create quasars. The ones that do are typically in the process of rapidly accreting material, and they exist in galaxies with enough fuel to sustain this high-energy activity. However, once a quasar goes dormant, it can become a normal elliptical galaxy, its black hole still present but no longer emitting the intense radiation that defined it during its quasar phase. The energy output of quasars is so immense that it can sometimes have a profound effect on the surrounding universe. The radiation emitted by a quasar can ionize nearby gas, creating large regions of hydrogen gas that have been stripped of their electrons. This process, called reionization, played a critical role in the early history of the universe. Quasars were a major source of this reionizing radiation, helping to change the state of the universe from a foggy, opaque cloud of gas to the transparent space we observe today. The light from the most distant quasars has taken billions of years to reach us, which means that when we observe them, we are actually seeing them as they were in the early stages of the universe. This gives scientists valuable insight into the conditions that existed in the distant past and helps them to understand how galaxies, black holes, and even the universe itself evolved. Blazar beacons, when black hole jets aim at Earth. Blazars are an exceptional class of active galactic nuclei, where the black hole at the center of the galaxy is actively consuming matter, resulting in high-energy emissions. The key characteristic that makes a galaxy a blazar is the orientation of its jets. Normally, the jets from a black hole's accretion disk are expelled in opposite directions along the black hole's rotational axis. In blazars, however, the axis of these jets happens to be aligned with our line of sight. This alignment leads to a phenomenon known as relativistic boosting, where the jet appears far brighter and more energetic than it would if it were pointing in any other direction. The reason for this dramatic increase in brightness is tied to the relativistic effects that occur when material is traveling at nearly the speed of light. As the jet points directly toward Earth, the light emitted by the particles in the jet is boosted due to their high speed. Essentially, the light waves from the jet are compressed in the direction of motion, making the emission appear much more intense than it would be if viewed from the side. This effect is a direct result of the physics of special relativity, which states that the faster an object is moving toward an observer, the brighter it appears. Blazars are among the most energetic and luminous objects in the universe. Their jets can release enormous amounts of energy, far exceeding that of the black hole's accretion disk itself. This is because the energy released in the jet is focused directly toward Earth, amplifying its power. In fact, the energy output from a blazar can rival the combined light of entire galaxies, making them some of the brightest objects we can observe across vast distances. Unlike other active galactic nuclei, which tend to emit steady radiation, the brightness of a blazar can fluctuate significantly over short periods of time, sometimes even within a matter of hours or days. This variability is a result of the extreme conditions in the jet, where particles are being accelerated to relativistic speeds and constantly interacting with each other and the surrounding environment. These interactions cause the emission from the jet to change rapidly, making the blazar appear to flicker or pulse with a rhythmic intensity. Because the jets in these systems are aligned with our line of sight, we can study the innermost regions of the black hole's accretion disk with incredible detail. The fluctuations in the brightness of the jet allow scientists to probe the complex physics that governs the flow of material around a black hole and the mechanisms that lead to the formation of such powerful jets. In particular, the rapid changes in the jet's intensity suggest that the material near the black hole is undergoing extreme processes, such as shock waves and magnetic field fluctuations, that are responsible for producing the observed radiation. The energy emitted by a blazar is not just limited to visible light. They emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The lower energy emissions, such as radio waves, are typically produced by the synchrotron radiation from charged particles moving in magnetic fields. However, as the particles in the jet gain even more energy, they can produce higher energy radiation, such as X-rays and gamma rays. In some cases, the jet's energy output can be so intense that it produces gamma ray bursts, short, high-energy flashes that are capable of reaching Earth from billions of light years away. These high-energy emissions are often seen in blazars that are actively feeding. Because blazars are often located at the centers of distant galaxies, they serve as cosmic beacons that allow scientists to study the distant universe in great detail. Their extreme luminosity makes them visible from billions of light years away, providing a window into the far reaches of space. By studying the properties of the jets, astronomers can learn about the early universe, the growth of supermassive black holes, and the evolution of galaxies. As the light from a blazar travels across the universe, it can be affected by the material it encounters along the way. The intergalactic medium can absorb and scatter light, altering its properties by the time it reaches Earth. By analyzing the light from blazars, scientists can learn more about the density and composition of the universe's intergalactic medium, as well as the large-scale structure of the universe itself. One of the most famous blazars is the quasar 3C 279, located over 5 billion light-years away. 3C 279 is one of the brightest and most well-studied blazars in the sky, with its intense radiation making it a key object for astronomers. The variability of its emission has been studied extensively, and scientists have used it to test the theories of relativistic jets and the behavior of supermassive black holes. In recent years, astronomers have also discovered other blazars in different wavelengths, including gamma rays, using observatories like the Fermi Gamma Ray Space Telescope. Blazars can also be used to probe the nature of dark matter and dark energy. These mysterious substances make up a significant portion of the universe's mass-energy content, but their properties remain largely unknown. By observing how light from a blazar is altered by the intergalactic medium, scientists can infer the presence of dark matter and dark energy, as well as measure their effects on the propagation of light. Blazars, in this sense, serve as tools for cosmological investigations, providing insights into some of the most fundamental questions about the nature of the universe. Tidal disruption events. Stars torn apart by black holes. When a star ventures too close to a supermassive black hole, the difference in gravitational pull between the near and far sides of the star becomes overwhelming. This is the force known as tidal gravity. The side of the star closer to the black hole feels a much stronger gravitational force than the side farther away. As a result, the star begins to stretch out, much like an elongated rubber band. This stretching increases dramatically as the star gets even closer, until it eventually breaks apart. The result is nothing short of spectacular. As the star disintegrates, a burst of radiation floods space. This radiation comes in many forms, but the most prominent are ultraviolet and X-rays, which are produced by the intense heat and friction generated as the star's material is torn apart and accelerated. These tidal disruption events, or TDEs, are fleeting one-off events. Unlike the steady, ongoing accretion of material that powers the black hole's more familiar jet systems, tidal disruption events are dramatic and transient. Once the star is torn apart, its material is not immediately swallowed by the black hole. Instead, much of it is scattered into space, with some falling into the accretion disk, causing a temporary spike in its activity. The energy released during a TDE can be staggering. For a brief period, the flare produced by the event can outshine the entire host galaxy, sometimes by a factor of several hundred times. This makes TDEs some of the most energetic and dramatic phenomena in the universe. In fact, the energy released can be so intense that it creates a luminosity that is brighter than the combined light of all the stars in the galaxy. For a few weeks or months, the event can be a cosmic beacon, visible across vast distances. But what causes the star to come so close to the black hole in the first place? In many cases, the star's orbit around the black hole is altered by interactions with other stars, or by the gravitational pull of nearby objects. In some scenarios, a star may pass too close to the black hole during a close encounter, while in others, it may be a rogue star that is drawn into the black hole's gravitational well by chance. Whatever the cause, once the star crosses the tidal radius, the distance from the black hole at which the tidal forces become strong enough to tear it apart, the event becomes inevitable. As the star is torn apart, the gas and plasma that once made up its core and outer layers are ejected outward in a rapidly expanding cloud. This ejected material is typically heated to incredibly high temperatures, producing a flash of radiation that can be detected by telescopes. The star's remnants can also be carried away by powerful winds and shocks, spreading the debris across the surrounding space. The energy from the explosion can even cause shockwaves to ripple through the surrounding gas and dust, disturbing the interstellar medium and causing it to heat up and compress. The radiation emitted during the event provides valuable clues about the black hole's environment, including the density and composition of the surrounding gas, the shape of the black hole's accretion disk, and the dynamics of the event itself. In many cases, astronomers have used these flares to study the properties of the black hole, such as its mass, spin, and accretion rate. By analyzing the way the radiation from the flare changes over time, scientists can learn about the physics of the accretion process and how the material around the black hole behaves under such extreme conditions. The material ejected during the event can mix with the gas and dust in the galaxy, enriching the interstellar medium with heavier elements. The distribution of these elements can have a significant impact on the future evolution of the galaxy. The exact mechanisms that govern the way a star is torn apart and the precise nature of the radiation emitted during the flare remain subjects of intense research. Some of the most exciting questions concern the way in which material from the disrupted star is redistributed around the black hole. Does the star's material form a stable accretion disk, or is it ejected into space in a more chaotic manner? How do the jets and outflows created by the black hole interact with the surrounding gas? And how can we better observe and predict TDEs in distant galaxies? Unlike other cosmic phenomena, such as supernova or quasars, which can be observed over long periods of time, tidal disruption events are over in a matter of months or even weeks. By the time astronomers detect one, it may already be in its final stages, making it difficult to observe all aspects of the event. Gamma-ray burst, taxonomy, short, long, and the in-between. Most gamma-ray bursts, or GRBs, are generally divided into three categories based on their duration: short bursts, long bursts, and an enigmatic middle group. The duration of a burst is not just a simple measurement of time. It gives us significant clues about the underlying processes that cause the burst. The short bursts and long bursts are distinct in both their behavior and their origins, while the in-between category is a puzzle that has yet to be fully solved. Short gamma-ray bursts are typically less than 2 seconds long, with most lasting just a fraction of a second. These bursts are incredibly powerful, emitting vast amounts of energy in a very brief window of time. The origins of short GRBs have been linked to the violent merger of compact objects, typically neutron stars. When two neutron stars spiral toward each other and merge, the resulting explosion can send out intense waves of gamma radiation. Long gamma-ray bursts last up to several minutes. They are typically associated with the deaths of massive stars. Unlike short bursts, long GRBs occur when a massive star, one that is at least 30 times more massive than our Sun, reaches the end of its life. When such a star runs out of nuclear fuel, it collapses under its own gravity, triggering a supernova. This collapse leads to the formation of a black hole, and the intense release of energy during this collapse produces a long gamma-ray burst. Then there is the third, more mysterious category, the in-between bursts. These bursts last somewhere between the short and long categories, typically lasting anywhere from a few seconds to a few minutes. The mystery of these bursts lies in their uncertain origin. Their duration and the amount of energy they release suggest that they may be caused by a different kind of event, one that has yet to be fully understood. Some theories suggest that these intermediate duration bursts could be caused by the collapse of a star with a lower mass than those responsible for long bursts, but more research is needed to confirm this. Long gamma-ray bursts tend to occur in younger, more active galaxies, where the formation of massive stars is still happening. The presence of these bursts in young galaxies suggests that the processes that produce them are tied to the early stages of galactic evolution. Short bursts, on the other hand, are often found in older galaxies, where neutron-star mergers are more likely to occur as compact objects form and interact over time. Ultra-long gamma-ray bursts, sustained cosmic infernos. There exists a rarer subclass of GRBs that shatter the typical duration limits, the ultra-long gamma-ray bursts. These bursts can last for thousands of seconds, far exceeding the duration of the more common long bursts, and hint at unknown processes deep in the cosmos. The discovery of ultra-long GRBs challenges our understanding of stellar evolution and the events that can trigger such sustained explosions. The first ultra-long GRB, GRB 111209A, was observed in 2011. It stayed bright for over an hour, gradually fading away. Since then, several other ultra-long bursts have been detected, but they remain mysterious and not fully understood. They do not align with the usual mechanisms that generate GRBs. One of the leading hypotheses for the origin of ultra-long GRBs is that they may be triggered by the collapse of an exceptionally massive star, such as a blue supergiant. Blue supergiants are large, hot stars that are in a relatively brief stage of their life cycle, burning through their nuclear fuel at an incredibly fast rate. When these stars exhaust their nuclear fuel, they are thought to undergo core collapse, leading to a supernova. But the collapse of these stars may not follow the usual pattern seen with other massive stars. Instead of a rapid collapse that produces a short gamma-ray burst, the star might go through a more gradual collapse, resulting in an extended explosion that produces a much longer GRB. Another possibility is that ultra-long GRBs could be caused by TDEs. As the star is torn apart, its material spirals into the accretion disk, which can heat up to extreme temperatures, emitting radiation, including gamma rays. In some cases, the disruption of the star might result in an explosion that lasts for an extended period, fueling the ultra-long gamma-ray burst. This prolonged energy release is not just a longer version of the typical gamma-ray burst, it is a fundamentally different phenomenon. In many cases, the energy of an ultra-long GRB doesn't come in the form of a single sharp pulse, but instead in a sustained flare that gradually fades over time. It points to an event that is not just explosive, but also prolonged, something that slowly builds up and sustains itself for a much longer duration. Just like long GRBs, ultra-long bursts are often found in distant galaxies, typically billions of light-years away. These galaxies tend to be star-forming regions, where massive stars are born and live out their brief explosive lives. But ultra-long GRBs are not tied to a particular type of galaxy. They seem to occur in galaxies with a range of properties, from the more typical star-forming galaxies to those that have more unusual features. This suggests that the mechanism behind ultra-long GRBs might not be as closely tied to the specifics of a galaxy's environment as it is to the characteristics of the star or object that triggers the burst. Because they last so much longer than typical GRBs, they are harder to detect using traditional gamma-ray observatories, which are often designed to catch short bursts that last only a few seconds. Ultra-long bursts require more continuous monitoring, as their extended duration means that they can fade away slowly. As a result, researchers have to rely on a combination of satellite-based observatories and ground-based telescopes to detect and track these events. The increasing sensitivity of these instruments, especially the next-generation telescopes, will likely lead to more discoveries of ultra-long GRBs and will provide more data to help scientists understand their origin. While the collapse of a massive star typically results in a supernova or a black hole, the extended nature of ultra-long GRBs suggests that some stars may experience a more prolonged death, one that radiates energy for a far longer time. Similarly, the possibility of TDEs being responsible for ultra-long bursts suggests that supermassive black holes play a much more active role in the dynamics of galaxies than previously thought. Cosmic string oscillations, hypothetical energy highways. Cosmic strings represent a possible feature of the very fabric of space-time itself. Imagine the universe as a vast and complex tapestry, where, at certain points, the fabric may not be perfectly smooth or uniform. Instead, there could be defects, extremely thin, one-dimensional objects that stretch across vast distances. These cosmic strings, if they exist, would be unlike anything we observe in our everyday experiences. They would not be solid objects in the conventional sense, but rather structures embedded in space-time that could cause ripples, twists, and disturbances. The concept of cosmic strings originates from the early days of the universe, during a period known as cosmic. This was a time when the universe expanded incredibly rapidly, and various defects may have formed as the universe cooled and settled into its current state. In some models of the early universe, cosmic strings were predicted to form as a result of phase transitions that occurred in the field governing the fundamental forces of nature. These strings are thought to be one of the possible remnants of these processes, representing a kind of topological defect that exists in space-time itself. These strings would not be static, but could vibrate or oscillate in response to changes in their environment or the forces acting upon them. As they oscillate, they could cause disturbances in the surrounding space-time. These disturbances would not be ordinary ripples of matter or radiation, but would instead be gravitational waves that propagate out from the string's movement. These waves would be different from those produced by the more familiar astrophysical events, such as the merging of black holes or neutron stars. Instead, they would be a consequence of the movement of the strings themselves. Movements that might occur on extremely small scales, but still have the potential to send ripples through the universe. The possibility of detecting these gravitational waves from cosmic strings has been the subject of much theoretical study. However, it remains purely speculative at this stage. No direct evidence of cosmic strings has been observed, and it's unclear whether they even exist. The oscillations of these strings could be incredibly faint, making them difficult to detect even with the most sensitive instruments available today. Additionally, the precise nature of the waves they might produce is still a subject of ongoing research. If cosmic strings do exist, they could serve as a unique probe into the conditions that prevailed during the universe's infancy. These strings might offer clues about the fundamental forces and fields that governed the early universe, allowing scientists to test various theories of particle physics and cosmology. The energy associated with cosmic strings would also be extraordinary. Because of their extreme density and the potential for high-speed oscillations, these strings could release vast amounts of energy. Some theorists speculate that if cosmic strings exist and oscillate as expected, they could even be responsible for some of the unexplained phenomena observed in the universe, such as high-energy cosmic events or mysterious gravitational wave signals. If a cosmic string were to undergo a rapid acceleration or encounter a region of intense gravitational interaction, it could send out a burst of gravitational waves that might be detectable by current or future observatories. While the strings themselves would be incredibly thin and difficult to detect, they could still have a profound effect on the surrounding matter. If a cosmic string were to pass near a massive object, such as a star or a black hole, it could distort the space-time around that object. These interactions could lead to changes in the orbits of nearby planets, stars, or even entire galaxies. In some models, cosmic strings are thought to be able to generate shock waves or other disturbances that could affect the formation and evolution of structures in the universe. Topology is a branch of mathematics that studies the properties of shapes and spaces that are preserved under continuous deformations, such as stretching or bending. The idea of a topological defect in spacetime is an extension of this concept, suggesting that the structure of spacetime itself could contain imperfections or discontinuities. Cosmic strings are a manifestation of these topological defects, representing areas where the usual smoothness of spacetime is disrupted. This idea connects directly to some of the most fundamental questions in physics, such as the nature of gravity, the geometry of the universe, and the behavior of spacetime at the most fundamental levels. If they do exist, the discovery of cosmic strings would represent one of the most significant breakthroughs in our understanding of the universe, offering a glimpse into the very fabric of spacetime itself. Dark matter, annihilation, invisible power sources. Dark matter accounts for roughly 27% of the universe's total mass energy content, making it far more abundant than ordinary matter, which makes up only about 5%. The rest of the universe, around 68%, consists of dark energy, which drives the accelerated expansion of the universe. Despite dark matter's abundance, it remains invisible to our most advanced telescopes, as it interacts primarily through gravity and possibly weak forces, but not through the electromagnetic forces that affect light. One theory about dark matter is that it might be made up of unknown particles, and that these particles could occasionally collide with each other. When dark matter particles collide, they might annihilate each other, much like matter and antimatter do in our everyday world, releasing a burst of energy in the form of gamma rays or other high-energy particles. If such annihilation events happen often enough, they could create detectable signals that could provide scientists with clues about the nature of dark matter. Researchers have been trying to detect the faint but potentially significant signals that might arise from these collisions. Gamma rays are particularly important in this search because they travel across vast distances without being absorbed or scattered, making them ideal messengers for distant and faint phenomena. The most commonly proposed dark matter candidates are weakly interacting massive particles, or WIMPs, and axions. These particles would have mass, but unlike ordinary matter, they would not interact much with normal matter. Their only significant interactions might be through gravity and the weak nuclear force. When two dark matter particles collide and annihilate each other, the energy released could take the form of gamma rays or other particles, depending on the specific properties of the dark matter particles involved. One of the most promising targets for detecting dark matter annihilation is the center of our galaxy, the Milky Way. This region is thought to contain a high concentration of dark matter, so if dark matter particles are indeed annihilating each other, the galactic center could be an ideal location to observe such events. Some scientists have pointed to the discovery of an unusual diffuse gamma ray emission from the galactic center as a possible signature of dark matter annihilation. This emission is distinct from the gamma rays produced by known sources, such as stars, supernova remnants, and black holes, and it has characteristics that resemble what might be expected from dark matter interactions. Many researchers have cautioned that the gamma ray signal from the galactic center could be caused by other astrophysical processes, such as cosmic rays interacting with gas in the region, rather than dark matter annihilation. There are also other possible sources of gamma rays in the galactic center, including pulsars. In addition to the search for gamma rays from dark matter annihilation, there are other methods being explored to detect dark matter directly. For example, experiments on Earth attempt to directly measure the interactions of dark matter particles with ordinary matter. These experiments typically involve placing highly sensitive detectors deep underground to shield them from cosmic radiation and other background noise. If a dark matter particle interacts with the detector, it might produce a tiny but detectable signal. However, even these direct detection experiments have not yet yielded any conclusive evidence of dark matter particles. While the search for gamma rays from dark matter annihilation is still ongoing, there are also theoretical challenges to interpreting these signals. One of the difficulties is that dark matter is expected to be distributed relatively smoothly throughout the universe, so it might be hard to distinguish any annihilation signals from the background radiation emitted by other sources. For example, gamma rays from cosmic rays interacting with gas or dust in the interstellar medium could potentially mimic the signal from dark matter annihilation. If scientists can confirm that dark matter particles are annihilating and producing detectable signals, it would be one of the most important discoveries in modern physics. Not only would it provide direct evidence for the existence of dark matter, but it would also open the door to new physics beyond the Standard Model. The properties of dark matter particles, their interactions, and the process of annihilation could reveal a wealth of information about the fundamental forces and particles that govern the universe. Furthermore, dark matter annihilation could provide insights into the formation and evolution of galaxies. If dark matter plays a central role in shaping the structure of galaxies, understanding how it interacts and annihilates could help explain the formation of galaxy clusters, the distribution of matter in the universe, and even the overall fate of the cosmos. The possibility that dark matter could influence the energy budget of galaxies, regulate star formation, or even produce powerful gamma-ray flares adds a new layer of complexity to our understanding of cosmic evolution. Galaxy cluster collisions, colossal cosmic rammers. When galaxy clusters collide, it is a spectacle of unimaginable scale and violence. These enormous cosmic structures, each containing thousands or even tens of thousands of galaxies, are the largest known gravitationally bound systems in the universe. Their collisions are far more than simple encounters between individual galaxies. They are massive, sprawling events that can stretch across millions of light years. The result is a cosmic crash that not only involves the stars within the galaxies, but also the vast clouds of hot gas and the mysterious dark matter that permeates the cluster. When galaxy clusters collide, they create one of the most extreme and awe-inspiring phenomena in the universe. As galaxy clusters draw closer to one another, their constituent galaxies start to interact. But it's not just the galaxies themselves that are involved in these collisions. It's the vast clouds of gas that they carry with them. These clouds are typically filled with high-energy particles, glowing brightly in X-rays as they reach temperatures of tens of millions of degrees. When clusters collide, the gas clouds within them slam into each other, compressing and heating to even higher temperatures. This process releases an enormous amount of energy in the form of X-rays, making the collision of galaxy clusters one of the most violent and energetic events in the universe. While the galaxies themselves might pass through each other largely unaffected due to the vast distances between stars, the gas that fills the clusters is far more likely to interact. This leads to intense shockwaves as the hot gas is compressed, often resulting in dramatic bursts of energy. The sheer scale of the collision means that the gas is not only heated, but also stirred, creating turbulent flows and creating a complex, chaotic environment. In some cases, the temperature of the gas can reach up to 100 million degrees Celsius or more, creating a furnace of unimaginable proportions. The energetic release from these collisions can outshine the combined energy output of all the stars in the entire cluster. During a collision, the dark matter is thought to pass through the interacting galaxies and gas relatively undisturbed, but its gravitational influence can still be felt. As a result, the dark matter halos that surround each cluster may shift and merge as the two clusters collide, helping to shape the dynamics of the event. When galaxy clusters collide, the dark matter halos from each cluster move in different ways than the gas and stars. This can leave behind telltale signs in the distribution of galaxies and gas, giving astronomers clues about the properties and behavior of dark matter. Observing how dark matter behaves during these collisions has provided some of the most significant insights into the nature of this mysterious substance. One of the most famous examples of a galaxy cluster collision is the Bullet Cluster, a pair of galaxy clusters that collided at high speed. The Bullet Cluster provides an unprecedented view of how dark matter behaves during such a collision. In this case, the visible gas from the clusters interacted strongly and was slowed down by the collision, creating a shock front of high-temperature gas. Meanwhile, the dark matter passed through the collision without being affected. This resulted in a separation between the visible matter and the dark matter, providing compelling evidence for the existence of dark matter and giving scientists a glimpse into its elusive nature. Galaxy cluster collisions also play a crucial role in the broader evolution of the universe. The tremendous energy released during these collisions can trigger the formation of new stars as the gas is compressed and cooled. The shock waves that ripple through the gas can push the gas together, causing it to collapse and ignite new star formation. This process, known as starburst, can lead to the creation of thousands of new stars in a relatively short amount of time. At the same time, the collision can also disrupt existing star formation. As the gas is heated and stirred up, it can prevent gas from collapsing into new stars, effectively halting or suppressing star formation in certain regions of the cluster. In some cases, the result is a galaxy cluster that is less efficient at creating new stars. When galaxy clusters collide, they release vast amounts of energy in the form of X-rays and other radiation that ripples through space. These ripples can affect the surrounding environment, including other galaxy clusters, and may even influence the way that galaxies and clusters evolve over billions of years. By observing galaxy cluster collisions, scientists can learn more about the larger-scale structure of the cosmos, including the distribution of galaxies, the growth of cosmic structures, and the overall fate of the universe. In addition to the observational work, scientists are also developing new models and simulations to better understand the mechanics of galaxy cluster collisions. These simulations use powerful computer algorithms to model the behavior of gas, stars, and dark matter during a collision, helping to provide a clearer picture of what happens during these high-energy events. By comparing these models to real-world observations, astronomers can refine their understanding of galaxy clusters and improve their predictions for how these collisions might unfold in the future. Gravastars and other exotic compact objects. While black holes have long been the go-to model for describing the most extreme gravitational environments, gravastars suggest that there might be something even stranger lurking in the final stages of a star's life. A compact object that doesn't quite behave like a black hole, but still presents a near impossible density. In the familiar story of stellar collapse, when a massive star runs out of fuel, its core implodes under the force of its own gravity, potentially forming a black hole. But the gravastar offers a twist on this narrative, suggesting that instead of collapsing to a point where gravity becomes infinite, the core might stabilize in a new way, creating a different kind of singularity, a vacuum bubble that forms at the center. The central concept behind a gravastar is built upon the idea of quantum mechanics and exotic states of matter. When a star collapses, the idea is that instead of matter compressing to the point of infinite density, the collapse halts before reaching that critical point, and the matter in the star compresses to a very dense state, where quantum forces come into play, stopping the collapse. This dense exotic matter might form a shell or bubble, enclosing a vacuum in the center, which is where the term vacuum bubble comes from. This structure creates an object that is incredibly compact, much like a black hole, but with some significant differences. For one, a gravastar is not a true singularity. Instead, it has an outer shell that is thought to act as a boundary where exotic matter and energy interact in complex ways. The inside of a gravastar would be a region of extremely low density, a kind of empty space in the center where quantum effects take over. The outer layer of a gravastar is thought to be composed of a form of exotic matter that would be held together by extremely strong forces, yet it would not collapse into the dense singularity we associate with black holes. Instead, it forms a dense shell that could maintain its stability due to the balance of energy and quantum pressure within. In black holes, the event horizon marks the point of no return, where any object crossing it cannot escape the pull of the black hole's gravity. But in a gravastar, the boundary is not quite so absolute. The collapse halts before the formation of a true event horizon, and instead, the object remains a stable, albeit exotic, configuration. This subtle difference leads to a crucial distinction. While a black hole might suck in everything that crosses its event horizon, a gravastar would allow light and information to escape from its outer boundary. The interior of a gravastar is an even more mysterious region. Some models suggest that it might contain exotic particles or fields, such as dark energy or unknown forms of quantum matter. These would be tightly packed within the star's outer shell, creating a unique balance between the forces trying to collapse the star and the forces resisting that collapse. While still a theoretical concept, this means gravastars could represent a new type of object that challenges the fundamental ideas about the end states of collapsed stars. Gravastars also offer an alternative to the problem of what happens at the center of black holes. In black hole models, once something crosses the event horizon, it is doomed to eventually reach the singularity, a point of infinite density. But if gravastars exist, they would offer a scenario where the matter does not actually fall into an infinitely dense point, but instead creates a highly compressed yet stable state. The exact nature of what would happen to matter inside a gravastar is not entirely clear, but it opens up fascinating possibilities for what might lie at the heart of some of the universe's most mysterious objects. Gravastars would likely be very difficult to distinguish from black holes, at least at a distance. Both would be extremely compact, with immense gravitational fields and the ability to bend light and space-time around them. In fact, many of the observed phenomena associated with black holes, such as gravitational lensing or the accretion of matter into a compact region, might also be present around a gravastar. However, unlike black holes, a gravastar would not have an event horizon. Another exotic class of objects that challenges the concept of black holes comes from the idea of fuzzballs. This theory, originating from string theory, suggests that what we think of as a black hole might actually be a highly complex, tangled ball of strings at a microscopic level. In this model, the traditional notion of a singularity is replaced by a complicated structure made of strings that spread out over a vast region, avoiding the infinite density of a true singularity. A fuzzball would still produce the same kinds of gravitational effects that we associate with black holes, but instead of a point-like singularity, there would be a much more diffuse and complicated structure. If gravastars or fuzzballs exist, they would represent a radical departure from the traditional black hole model. Instead of infinite density and event horizons, we would have compact objects with highly exotic properties, requiring us to rethink the fundamental mechanics of the universe. As of now, there is no direct observational evidence for their existence. The current models of black holes, particularly those involving the formation of event horizons and singularities, remain the most widely accepted, and much of the evidence we have, from gravitational waves to the shadow of the supermassive black hole in M87, supports the traditional black hole theory. Gravastars and other exotic compact objects represent a fascinating frontier. They highlight how little we truly understand about the final stages of stellar evolution and the deepest forces of the universe. While black holes remain the reigning champions of extreme gravity, these new ideas challenge us to look deeper and question the foundations of our understanding of space-time. Vacuum decay, the ultimate theoretical catastrophe. One of the most unsettling ideas in physics is the concept of vacuum decay. This theory suggests that the very fabric of the universe, the vacuum state in which all of matter and energy exist, might not be as stable as we think. According to this idea, there could be a potential for a vacuum bubble to form, an area of space where the laws of physics are radically different from our current understanding. If such a bubble were to form, it could spread through the universe at nearly the speed of light, destroying everything in its path, including space itself. Quantum field theory suggests that the vacuum, the so-called empty space that seems to be devoid of anything tangible, is not truly empty at all. Instead, it is a seething, fluctuating field where particles and antiparticles constantly pop in and out of existence. This constant activity is called vacuum fluctuation, and it's this very nature of the vacuum that opens the door to the concept of vacuum decay. In simple terms, vacuum decay proposes that the vacuum of space, which is thought to be in a stable state, might actually be in a false vacuum. This false vacuum is a state of energy that is not the lowest possible energy configuration that space could exist in. The true vacuum, in contrast, would be the lowest energy state of the universe, and it is this true vacuum that could potentially cause catastrophic changes. If the universe were to transition from the false vacuum to the true vacuum, this would represent a massive universe-wide event, an event in which all of the fundamental forces, constants, and even space itself might be altered. In quantum mechanics, particles are often able to tunnel through barriers that they would not be able to surmount in the classical sense. For instance, instead of simply bouncing off an energy barrier, particles might pass through it, as if the barrier doesn't exist. This is a key feature of quantum behavior that allows for the possibility of the vacuum bubble. In theory, if there is a lower energy vacuum state, that is the true vacuum, the universe could tunnel from its current higher energy or false vacuum state into this new state. This transition could trigger a catastrophic change in the laws of physics, where things like gravity, electromagnetic forces, and even the very constants of nature might be unrecognizable. In effect, the vacuum decay would reset the universe, erasing everything that we know and causing the laws of physics to operate in a completely different way. If such a bubble of true vacuum were to form, it would cause the destruction of all matter and energy as we understand it. Within this bubble, space itself would cease to behave in the same way. The result is that everything, including time itself, would be obliterated. In this sense, vacuum decay represents an almost ultimate form of cosmic catastrophe. While most catastrophic events we can imagine, such as supernovae or black hole collisions, still operate under the known laws of physics, vacuum decay represents an event that would obliterate the very foundation of those laws. The collapse of the space-time fabric and the disintegration of all fundamental forces would make any kind of recovery or reformation impossible. It's not a catastrophe that we could observe from a safe distance. It's one that, once it begins, would be total, irreversible, and all-encompassing. There would be no one left to study its effects, no one to try and rebuild after the fact. Once the false vacuum is destabilized and the true vacuum begins to form, the bubble would grow at nearly the speed of light, meaning no object, no matter how advanced, could escape its influence. This expansion would be an unrelenting, unstoppable force, erasing every bit of matter and energy as it passed through. Stars, planets, galaxies, and everything else would be consumed by this expanding bubble of altered physics. It's difficult to imagine a disaster more extreme than this, as it would encompass every possible form of destruction, wiping the slate clean in an instant. Despite its mind-bending implications, the idea of vacuum decay is still very much a theoretical one. While it is mathematically consistent with the theories of quantum field dynamics, there is no direct evidence that such an event is likely to occur. In fact, the energy scale required for a vacuum decay event to happen is so high that it seems extremely unlikely that the universe is anywhere near a state where such a transition could occur. Many physicists consider it to be a highly speculative possibility, and some even argue that the universe might be in a true vacuum state already, meaning that the false vacuum idea simply doesn't apply. If the universe is truly in a false vacuum state, as the theory suggests, then how can we be certain that the current vacuum we experience is the only one that could exist? What happens if the constants of nature, such as the strength of gravity or the electric charge of particles, can be changed so radically? What does it mean for something to be stable in the first place if the stability of the universe is contingent on an unknown energy field? These are not just questions for physicists, but for anyone who wonders about the very nature of reality. If the universe is not as stable as we believe, how much of our understanding of existence is merely an illusion? Whether it's a true threat to the survival of the universe or simply an artifact of our current limited understanding, the concept of vacuum decay underscores the deep mysteries that lie beneath the surface of the cosmos, waiting to be uncovered. Eternal inflation bubbles. Energy in the multiverse. While traditional inflation theory explains the rapid expansion of space during the earliest moments of the Big Bang, Eternal inflation theory proposes that inflation didn't end everywhere at the same time. Instead, in some regions of space, inflation continued indefinitely, leading to the creation of an infinite number of pocket or bubble universes, each with its own set of physical laws and constants. In the standard model of the Big Bang, the universe began as an incredibly hot and dense point, expanding outward in a process known as inflation. This inflationary period, lasting only a fraction of a second, stretched space-time faster than the speed of light, smoothing out the irregularities that would later form the galaxies, stars, and other structures of the universe. The idea is that this rapid inflation allowed the universe to expand exponentially, spreading the energy and material that would eventually form all that we see around us. However, eternal inflation takes this idea even further, proposing that inflation never fully stopped in certain parts of the universe. In fact, some regions have continued inflating for an eternity, generating a cascade of new, separate bubble universes. Each bubble forms its own universe, with its own properties, laws of physics, and fundamental constants. The regions where inflation continues are thought to be filled with an incredibly high energy field, the inflaton field. This field drives the eternal inflation process, keeping the bubbles expanding rapidly and separating them from one another, creating the multiverse, a vast collection of universes, each potentially distinct from our own in ways we cannot yet imagine. If eternal inflation is real, it means that our universe is not isolated or unique. Instead, it is just one of countless others scattered throughout a larger, ever-expanding multiverse. The space between these bubble universes would be filled with regions where inflation continues, making the multiverse almost impossible to detect or observe directly. The bubbles are separated by regions of inflating space that are so far away from one another that they are causally disconnected, meaning we could never travel to or even see these other universes. They are effectively beyond our reach, locked in their own little corners of the multiverse. The energy involved in this process is extraordinary. Within the bubbles, each universe forms with its own unique set of physical conditions, which could include different values for constants like the strength of gravity or the speed of light. These differences arise because each pocket universe is shaped by the energy fluctuations that occur during inflation. In some universes, the energy density might be incredibly high, while in others, it could be lower. Some universes might be filled with matter, while others could be completely empty. In this way, eternal inflation suggests that the variety of possible universes is essentially limitless, each with its own unique characteristics. Eternal inflation resolves certain paradoxes within our own universe, such as the problem of why the universe appears so uniform and isotropic, meaning the same in every direction, at large scales. The rapid expansion of inflation explains how distant regions of the universe could have come into thermal equilibrium and shared the same temperature, despite being too far apart to have exchanged information in the traditional sense. This smoothness and uniformity are precisely what we see when we look at the cosmic microwave background radiation. Eternal inflation further suggests that this kind of smoothness could be a common feature of many bubble universes in the multiverse, even if their individual properties are vastly different. How can we make sense of our own universe if it is merely a bubble in a much larger multiverse? Some bubbles may harbor life and complex structures, while others might be cold, dark, and empty. Could there be bubbles where the laws of physics are so radically different from our own that life, as we understand it, is impossible? The very idea of a multiverse challenges our understanding of existence. The nature of reality, the universe, and everything we know may not be confined to the limits of our observable universe. The possibility of an infinite number of universes existing simultaneously could mean that there are countless versions of our reality, each with its own variation on the physical laws we take for granted. If the multiverse exists, it may be completely beyond our ability to observe or explore in any meaningful way. Since we can only observe the part of the universe that is within our cosmic horizon, limited by the speed of light and the age of the universe, everything outside this observable region is effectively beyond reach. The bubble universes that form in eternal inflation are not connected to our universe in any observable way, making them fundamentally inaccessible to any kind of direct measurement or observation. This presents a challenge for scientists trying to test the theory of eternal inflation. How do you prove the existence of something that cannot be observed? Some have proposed that eternal inflation could leave behind signatures that might be detectable in the cosmic microwave background radiation, faint traces of the energy fluctuations caused by the formation of the bubbles. If these signatures exist, they might offer indirect evidence of the multiverse. But even these traces would be incredibly hard to find, and there is no guarantee that we would ever be able to detect them with our current technology. For now, the theory remains speculative, relying on mathematical models and indirect evidence rather than direct observation. Yet, despite the challenges, the idea of eternal inflation forces us to reconsider the nature of the cosmos and our place within it. The more we learn about the cosmos, the more we realize that our understanding of the universe is far from complete. Eternal inflation is one of the many possibilities that continue to stretch the boundaries of human imagination and our search for knowledge about the ultimate nature of existence. Computronium collisions, intelligence-driven energy releases. While the cosmos seems mostly defined by massive gravitational forces and energetic explosions, there's a realm of thought that blends the two elements, energy and information, into a single, unified concept. This realm might one day lead us to a strange and profound idea: computronium collisions. Computronium, a theoretical material, refers to a substance optimized for the processing of information. Imagine a world where not just computers, but the very fabric of matter itself is designed to process data at an incredible scale. This concept arises when we think about the future of computing and how advanced civilizations might harness and manipulate information. Computronium might someday be created by sophisticated technologies that can transform ordinary matter into structures capable of efficiently carrying out computations at the atomic or subatomic level. At its core, the idea of computronium collisions centers around the hypothesis that such materials, if they exist, could one day be harnessed in a way that fuses energy production and information processing in ways unimaginable today. This is more than just data crunching. It's about tapping into the very energy of computation itself, using material science to create a new frontier of high-energy physics. Theoretical models suggest that computronium could take forms beyond anything we can currently build. Instead of discrete systems like computers or chips, computronium would be a substance that, at its most basic, could manipulate the flow of information on a level that would rival the most advanced computing systems we can imagine. And yet, there's a deeper layer of speculation. If these systems were to collide, perhaps in an interstellar setting or during high-energy interactions, they might release energy in a way that we've never seen before. We already know that energy can be released from matter. The most obvious example is in nuclear reactions, where the binding energy of atomic nuclei is released during processes like fission and fusion. But what if, instead of dealing with simple matter, we could manipulate computational matter, material optimized for processing data, to create a new form of energy release? Imagine for a moment two slabs of computronium crashing into each other at high velocity. These slabs are not made of ordinary matter. Rather, they are composed of highly organized structures. One possible outcome of such a collision could involve the release of large amounts of energy in the form of radiation. But unlike traditional forms of radiation, this energy would be intricately tied to the computational processes occurring within the slabs of computronium. Essentially, the collision would disrupt the very fabric of the computational processes, triggering a release of energy that reflects the destruction of information itself. This energy would be a byproduct of the information processing systems within the slabs, making it an entirely new type of energy release, one that we've never observed in nature. Furthermore, such a collision could create shock waves through both physical space and the information network that spans the collision site. Just as a traditional explosion might produce heat, light, and sound, A computronium collision could generate a cascade of information processing anomalies, disrupting the local environment. The sheer amount of computation involved in such an event would result in a rapid, intense release of energy, potentially even creating localized bursts of high-energy particles or radiation that could be detectable across vast distances. Traditionally, the source of energy in cosmic events, be it in stars, black holes, or supernova, has been tied to the transformation of matter or the gravitational collapse of massive objects. But in the case of computronium collisions, the energy is released from the computational processes that occur within the material. The potential implications for such events are vast, as they could fundamentally change our understanding of energy, matter, and information. In terms of scale, computronium collisions would likely be most relevant in environments where extremely high energy events take place. These could include the cores of advanced civilizations, where massive computing systems might be used for purposes ranging from energy production to artificial intelligence or even large-scale simulations of the universe. Alternatively, such collisions might take place in intergalactic settings, where vast networks of computronium could be used by extraterrestrial civilizations to manipulate spacetime or harness energy on a cosmic scale. We currently have no means of creating computronium or any material like it, and the idea of triggering energy releases from pure computation is still a concept on the far edges of our technological aspirations. However, the idea opens up a pathway for thinking about the future of energy and intelligence. What if, in the distant future, advanced civilizations could not only harness the power of stars and black holes, but also control and manipulate matter itself for computational purposes? The idea of computronium collisions represents a marriage of high-energy physics and material science, one that might one day revolutionize our understanding of the cosmos. Causality engines, machines that mine temporal energy gradients. Imagine a machine that doesn't just manipulate the fabric of space or energy, but one that taps into the very flow of time itself. The concept of causality engines proposes that it's possible to extract useful work from the differences in time flow, known as time gradients, across different regions of space-time. These hypothetical devices would operate not by manipulating mass or space in the traditional sense, but by exploiting the passage of time in ways we currently cannot even begin to fathom. We've seen time travel depicted in movies and novels, where characters jump between past, present, and future with relative ease. But these portrayals usually focus on moving through time rather than using its flow as a resource. Causality engines, on the other hand, are a theoretical concept that imagines using the natural variations in how time passes to perform work, effectively turning the passage of time into a usable form of energy. In classical physics, time is usually treated as a constant. We experience it as a steady, continuous progression: seconds, minutes, hours, days, and so on. However, according to the theory of relativity, time is not a simple, unchanging backdrop. It's part of the dynamic fabric of space-time, which can be warped and distorted by massive objects or extreme forces. When objects move at high speeds or are located near massive gravitational sources, such as black holes, time itself can appear to slow down. This is known as time dilation, and it's been confirmed experimentally in many different ways. For example, atomic clocks on satellites in orbit tick slightly faster or slower than clocks on Earth due to the difference in gravitational fields, demonstrating that time is not the same everywhere in the universe. In regions where time flows differently, such as near massive objects like black holes or in the presence of strong gravitational fields, the flow of time can be manipulated to create gradients, areas where time passes at different rates. If a device could be designed to exploit these differences, it might be able to extract energy from the difference in the passage of time. In this sense, the causality engine would be harnessing a kind of temporal energy that flows between regions with different time rates. One potential mechanism for this idea involves a method similar to how a heat engine works. A heat engine typically takes in thermal energy from a hot reservoir, uses it to do work, and then expels the remaining heat into a colder reservoir. If time were treated as a form of energy, Analogous to heat, a causality engine could operate by taking advantage of a time gradient, areas where time is passing at different rates. The device would extract energy from the difference in how time flows in these regions, much like how a heat engine extracts work from temperature differences. It might then convert this temporal energy into a usable form, such as mechanical or electrical work. However, the engineering of such a device would be incredibly complex. Time gradients exist naturally in the universe, particularly near massive objects like stars and black holes. But creating a controlled, manageable gradient would be an entirely different challenge. This would require an in-depth understanding of both space-time manipulation and the creation of stable, artificial time distortions. It's not just a matter of creating a small black hole or other massive object to create a time differential. Rather, it would require an ability to manage and direct the time differences in a way that could generate useful energy. Furthermore, time manipulation would likely require extremely high energy processes, perhaps beyond what even current technologies can handle. The energy involved in creating a significant enough time gradient to harvest usable energy could be immense. It would likely need to be far greater than the energy required to create black holes or manipulate gravitational fields on a large scale, pushing us into a realm of physics that is currently speculative at best. If a civilization were able to build causality engines, they would be able to tap into a completely new form of energy, one that doesn't depend on mass or space. Time itself, as a resource, is something fundamentally different from what we are used to. For instance, imagine an artificial environment, perhaps a massive spacecraft, that could be designed with regions where time flows slower than in the outside universe. In theory, energy could be harvested from the difference in time flow, powering the ship or its systems without relying on traditional fuels. A spaceship traveling near a black hole would experience time dilation, with time passing more slowly for those on board compared to people far away. If the ship were designed to harness this difference, it might be able to use the time differential to generate power, or even to alter its velocity or trajectory by manipulating the flow of time around it. In this sense, causality engines could unlock new possibilities in energy generation and transportation. Rather than relying on the physical constraints of fuel, propulsion, and traditional energy sources, they could use the structure of space-time itself as an energy source. Such a device might not even need to interact directly with the material world in the same way conventional technologies do, instead tapping into the fundamental properties of time and space-time to extract energy. However, we must also consider the potential risks of manipulating time on such a scale. Disturbing the flow of time, even in seemingly small ways, could have profound consequences, potentially affecting the very structure of reality. For example, altering time in one part of a system could cause unexpected effects in other regions. The stability of events could be compromised, leading to paradoxes or even the breakdown of causality. In the worst-case scenario, manipulating time could unravel the relationships between cause and effect, leading to unpredictable outcomes on a universal scale. Time manipulation on a large scale could distort the very fabric of space-time, creating regions where past, present, and future become indistinguishable. This could open up entire new realms of science and physics, but it would also challenge our basic assumptions about how the universe works. The flow of time, as we understand it, is a cornerstone of our reality. Altering or controlling it could lead to fundamental changes in how we perceive existence itself. Moreover, the idea of using time as a resource would introduce questions about its conservation. In traditional thermodynamics, the conservation of energy is a well-established principle. Energy cannot be created or destroyed, only transformed. But what happens when energy is tied to the passage of time? If a causality engine could extract work from time, would that mean the engine is robbing time itself of its natural flow? And if time could be harvested in such a way, could that lead to the depletion or distortion of temporal reality? While we are far from being able to build such devices, The concept offers tantalizing glimpses of the unimaginable potential hidden in the fabric of space-time. If a civilization were ever able to develop the technology to manipulate time itself, the scale of their achievement would be on a level that far surpasses even our most advanced ideas of engineering and energy production. Would you like to hear more about these sorts of speculative and wild power sources? Share your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.